Completeness. Let f less than or equal to be an ordered field, and let S be a non-empty subset of F. We say that S is bounded above if there is an element M in F such that for all S in S, S is less than or equal to M. Each such number M is called an upper bound of S. In words, an upper bound of a set S is simply an element from the field that is at least as big as every element in S. Similarly, we say that S is bounded below if there is an element K in F such that for all S in S, K is less than or equal to S. Each such number K is called a lower bound of S. In words, a lower bound of a set S is simply an element from the field that is no bigger than any element in S. We will say that S is bounded if it is both bounded above and bounded below. Otherwise, S is unbounded. A least upper bound, or supremum, of a set S is an upper bound that is smaller than any other upper bound of S. And similarly, a greatest lower bound, or infimum, of S is a lower bound that is larger than any other lower bound of S. Let's look at some examples. Let F less than or equal to be an ordered field with Q, the field of rationals, being a subset of F. What we have in mind here is that the ordered field F should either be Q, the ordered field of rationals, or R, the ordered field of reals. So you may want to keep one of these fields or both of these fields in mind as we go through these examples. I realize we haven't formally defined the field of real numbers, but you probably have a pretty good intuitive understanding of what they are, since that's the field you've been using for all arithmetic and algebra since elementary school. Okay, so number one, let's let S equal the set consisting of the numbers 1, 2, 3, 4, and 5. This set is bounded. 5 is an upper bound of this set S, and any number larger than 5 is also an upper bound of S. But 5 is special in the sense that there are no upper bounds smaller than it. 5 is the least upper bound, or supremum, of this set S. And we write sup S equals 5 for the supremum of S equals 5, or the least upper bound of S is equal to 5. 1 is a lower bound of S. And any number smaller than 1 is also a lower bound of S. But again, 1 is special in the sense that there are no lower bounds larger than it. 1 is the greatest lower bound, or infimum, of S. And we'll write inf S equals 1 for the infimum of S equals 1, or the greatest lower bound of S is equal to 1. Another example, let's let T equal the set of X in F such that -2 is less than X and X is less than or equal to 2. This is another example of a bounded set. The supremum of T, or the least upper bound of T, is 2, and the infimum of T, or the greatest lower bound of T, is -2. How about this set? U equals the set of X in F such that X is less than -3. This set is bounded above, but it's not bounded below, and therefore it's unbounded. The supremum of this set is -3, and it has no infimum because it's not bounded below. One more example. The set V equals x in f such that x squared less than 2 is bounded above. Let's look at this carefully. V is bounded above by 2 because if x is greater than 2, then x squared is greater than 4. Now, since we haven't proved it, you should actually verify carefully here that whenever a and b are positive numbers in an ordered field, then if a is greater than b, that implies that a squared is greater than b squared. And that's what we used here to say that if x is greater than 2, then x squared is greater than 4. Now, 4 is greater than or equal to 2. So therefore, if x is greater than 2, we have that x squared is greater than or equal to 2, and therefore x is not in the set V. Using the same kind of reasoning, we could show that any number greater than 2 is also an upper bound of this set V. The big question is 2 the least upper bound of V? And the answer is no, it's not. For example, 3/2, which is a number less than 2, is also an upper bound, right? Because if x is greater than 3/2, then x squared is greater than 9/4, which is greater than or equal to 2. So the big question is, does V have a least upper bound? It turns out that a least upper bound M of this set V would satisfy m squared is equal to 2. Now, this statement, although it seems reasonable, it's actually quite difficult to prove this, and we'll leave this as a challenging exercise in case you're interested in trying to go through the argument as to why this is true. It is challenging, though. Now, if F is the field of rational numbers, then this number m does not exist by theorem 5.6. Remember that theorem 5.6 says there does not exist a rational number a such that a squared is equal to 2. So if we want an ordered field F containing Q where m does exist, we can insist that F has the property that any set which is bounded above in F has a least upper bound in F. There actually is a unique such ordered field called R, the ordered field of real numbers. Going back to the 4 examples we did, I just want to point out that we didn't do these rigorously. We stated what the supremum and infimum was of each one, if they existed, but we didn't prove that those values were correct. So let's go ahead and do one in detail. Let's take the third one here, and we'll do this example carefully. So theorem 5.7, let U be the set of x in F such that x is less than -3. Then the supremum of U, or the least upper bound of U, is -3. So before we write out the proof in detail, let's go through an analysis to help us understand what's going on. We need to show that -3 is an upper bound of U, and that any number less than -3 is not an upper bound of U. That -3 is an upper bound of U follows immediately from the definition of U, right? Because U consists of all the elements of F that are less than -3. So that part's easy. The harder part of the argument is showing that a number less than -3 is not an upper bound of U. If A is less than -3, we simply need to find some number x between A and -3. Here's a picture of some number A that's less than -3, and we want to prove that that number is not an upper bound of the set U. Notice that A can be very close to -3, And we don't know exactly what A is. We know only that it's less than -3. So we need to be careful how we choose X. The most natural choice for X would be to go midway between A and -3. In other words, we can take the average of A and -3. So we will let X equal 1/2 A plus -3. Then we just need to verify that A is less than X and that X is in U, or equivalently that X is less than -3. Let's go through the details. If X is in U, then X is less than -3 by definition, and so -3 is an upper bound of U. That's the easy part. Suppose that A is less than -3. Here's the picture again. This statement is equivalent to the statement -A minus 3 is greater than 0. So that's the one we're going to use. We want to show that A is not an upper bound of U. To do this, we let X equal 1/2 of A minus 3. There it is in the picture. Notice it's midway between A and -3. Now, 1/2 can be rewritten as 2 to the minus 1, or 2 inverse. And A minus 3 can be rewritten as A plus -3 by the definition of subtraction. X is in the field F because F is closed under addition and multiplication, and the multiplicative inverse property holds in F star. We will show that X is between A and -3. So let's start by showing that A is less than X. To do that, we look at X minus A. Using a simple substitution, we can replace X by 1/2 A minus 3. And then I'm going to use the standard advanced calculus trick and rewrite A as 1/2 times 2A so that we could use the distributive property and pull out the 1/2. And now we can use commutativity of addition to interchange the -3 and the -2A. And we could combine A minus 2A to get -A. So we have that X minus A is equal to 1/2 times -A minus 3. Now, 1/2 is greater than 0 by theorem 5.4. Remember that theorem 5.4 said that if F less than or equal to is an ordered field and X is an element of F with X greater than 0, then 1 over X is greater than 0. So since 2 is greater than 0, 1/2 is also greater than 0. Now, -A minus 3 is greater than 0. That's our assumption. That's what we're supposing right in the beginning here. So it follows that X minus A is greater than 0, right? Because the product of two positive numbers is positive. And therefore, X is greater than A. Now for the second part of showing that X is less than -3, we start with -3 minus X. Do the same substitution. We replace X by 1/2 A minus 3. Standard advanced calculus trick again. Rewrite -3 as 1/2 times -6. Use the distributive property to pull out the half. And using commutativity and associativity of addition, we could combine the -6 and the 3 to get -3. And once again, since 1/2 is greater than 0 and -A minus 3 is greater than 0, it follows that -3 minus X is greater than 0. And therefore, X is less than -3. Thus, X is in the set U. So we found an element X in U, because X is less than -3, with A less than X. This shows that A is not an upper bound of U. It follows that -3 is the least upper bound of U, or the supremum of U. An ordered field F less than or equal to has the completeness property if every non-empty subset of F that is bounded above in F has a least upper bound in F. In this case, we say that F less than or equal to is a complete ordered field. Theorem: there is exactly one complete ordered field, up to renaming the elements. So there are lots of ways to describe the unique complete ordered field, but all of them are essentially the same thing. The technically correct way to say this is that there is exactly one complete ordered field up to isomorphism. We use the symbol R for the unique complete ordered field guaranteed to exist by theorem 5.8. R is called the complete ordered field of real numbers. Okay, let's prove a couple of theorems about the complete ordered field of real numbers. The first one is called the Archimedean property of R, and it says for every real number x, there is a natural number n such that n is greater than x. In other words, the Archimedean property says that the set of natural numbers is unbounded in the reals. In particular, the set of natural numbers is not bounded from above in the set of real numbers. We will prove this theorem by contradiction using the completeness property of the reals. If we wrongly assume that the set of natural numbers is bounded from above, then the completeness property of the reals gives us a least upper bound x. Since x is a least upper bound, x minus 1 is not an upper bound. Do you see the problem yet? If x minus 1 is less than a natural number little n, then x is less than n plus 1. But then x is not an upper bound for the set of natural numbers, contrary to our assumption. Let's write out the details now. Proof. Suppose toward contradiction that n is bounded from above. By the completeness property of the reals, x equals the supremum of n, or the least upper bound of n, exists. Since x minus 1 is not an upper bound for n, there is a natural number little n such that x minus 1 is less than n. Then we have x. Using the standard advanced calculus trick, we could write x as x plus negative 1 plus 1. And then using associativity, we could write that as x minus 1 plus 1, which is less than n plus 1. Since n is closed under addition, n plus 1 is a natural number. So x is not an upper bound for n, contradicting the fact that x equals sup n. It follows that n is not bounded from above. So, for every real number x, there is a natural number n such that n is greater than x. One more theorem, the density theorem. This says that if x and y are real numbers with x less than y, then there is a rational number, little q, with x less than q less than y. In other words, the density theorem says that between any two real numbers, we can always find a rational number. We say that the field of rational numbers is dense in the field of real numbers. To help understand the proof, let's first run a simple simulation using a specific example. Let's let x equal 16/3 and y equal 17/3. We begin by subtracting to get y minus x equal to 1/3. This is the distance between x and y. We wish to find a natural number n such that 1 over n is smaller than this distance. In other words, we want 1 over n less than 1/3, or equivalently, n greater than 3. So we can let n be any natural number greater than 3. Let's say n equals 4. We now want to shift 1 over n equals 1/4 to the right to get a rational number between x and y. We could do this as follows. We multiply n times x to get nx. So n is 4, x is 16/3. 4 times 16/3 is 64 over 3. We then let m be the least integer greater than nx. So m is 66 over 3. We choose 66 because it's the first number greater than 64, which is divisible by 3. And that reduces to 22. Finally, we let q equal m over n, which is 22 over 4, and we may as well reduce that to 11 over 2. And we did it. Indeed, 16 over 3 is less than 11 over 2, which is less than 17 over 3. You may want to check that these inequalities are true. Okay, let's go through the proof in detail. Let's first consider the case where 0 is less than or equal to x is less than y, and we'll let z equal y minus x. Okay, that's equal to y plus negative x. And since r has the additive inverse property and is closed under addition, z is a real number. Also, z is greater than 0 because x is less than y. By the Archimedean property, there is a natural number n such that n is greater than 1 over z. So 1 over n is less than z. You may want to check that these two inequalities are equivalent. By the Archimedean property once again, there is a natural number m such that m is greater than nx. Therefore, m over n is greater than x. And once again, you may want to check that these two inequalities are equivalent. So the set of m and n such that m over n is greater than x is non-empty. By the well-ordering principle, this same set has a least element. Let's call it k. Since k is greater than 0, because x is greater than or equal to 0 and n is greater than 0, and k is the least natural number such that k over n is greater than x, it follows that k minus 1 is a natural number and k minus 1 over n is less than or equal to x. Or equivalently, k over n minus 1 over n is less than or equal to x. Therefore, k over n is less than or equal to x plus 1 over n, which is less than x plus z, because 1 over n is less than z. And that's equal to x plus y minus x, right? Z is equal to y minus x, and that's equal to y. So we have that x is less than k over n, and k over n is less than y. Since k and n are natural numbers, we have that k over n is a rational number. Now we want to consider the case where x is less than 0 and x is less than y. By the Archimedean property, there is a natural number t such that t is greater than negative x. Then we have 0 less than x plus t less than y plus t. So x plus t and y plus t satisfy the first case that we just completed. Thus, there is a rational number q with q between x plus t and y plus t. It follows that x is less than q minus t is less than y. Since t is a natural number, negative t is an integer. Since the set of integers is a subset of the set of rational numbers, negative t is also a rational number. So we have q and negative t are both rational numbers. Since q is closed under addition, q minus t, which is q plus negative t, is also a rational number.